Even talk about Gaussian processes, I should explain and prove a very important and popular result about conditional Gaussian distributions, not Gaussian processes. So it's just elementary mathematics. So what I want to prove is that if we have a multivariate normal vector y, so we have mu and covariance sigma, then if you consider partitioning mu and y into mu1, mu2, and y2, y1, and y2 with a similar partition of the covariance matrix, then y1 conditioned on y2 is equal to a, we want to prove that this is the normal distribution having mu bar and sigma bar, where we want to prove that this mu bar is just mu1 plus sigma 1, 2, sigma 2, 2 minus 1, a minus mu2, and covariance is just sigma 1, 2 inverse of sigma 2, 2 and sigma 2, 1. So if we prove this result, then we will be able to talk about Gaussian process. So first we should prove this simple lemma about conditional distribution. So the proof is like this. There are many proofs in the literature and in the books, but I want to just write a proof that is less popular. So let x1 be the first partition and x2 is the second partition. By the way, this proof is very simple because we just need to define z, which is x1 plus ax2, and this a is just minus sigma 1, 2, sigma 2, 2 minus 1. And we can write the covariance of z and x2 to be the covariance of x1 and x2 plus covariance of ax2 and x2 by linearity. And so we know that we can just read that this is sigma 1, 2, and this is a times variance of x2. And you can simplify more and say that this is just sigma 1, 2, sigma 2, 2 minus 1, sigma 2, 2 equal to 0. So we understood that z and x2 are uncorrelated because they are jointly normal and they are independent. Now clearly expectation of z is equal to mu1 plus a mu2. Before talking about first I should write about the expectation. So we just simplify this. What is x1? As I said, it's z minus ax2. And then by linearity again, I can say that expectation of z condition on x2 minus e expectation of ax2 condition on x2. And this is just expectation of z minus ax2. And you can write it like this: mu1 plus a times mu2 minus x2. And finally mu1 plus sigma 1, 2, sigma 2, 2 inverse, x2 minus mu2. So it proves that for the mean of that conditional distribution. Now we just need to prove the same thing for the variance of that. But before that, we need to recall an elementary thing, that variance of x plus 1 y is equal to variance of x plus variance of y. This is so important, even beyond mathematics and finance, covariance of y and x. So, knowing this, we can work on the variance of x1 condition on x2, which is by definition, just by definition, z minus ax2 condition on x2. And just simplify that. These are very simple linear objects, so we just simplify that. The variance of ax2 condition on x2 is 0, and a covariance of zn minus x2 and minus covariance of zn minus x2 a prime. So this is 0, 0, 0. So what we are left with is variance of z condition on x2, which is just variance of z. Now, variance of x1 condition on x2 is equal to variance of z, which is equal to variance of x1 plus ax2. Just simplify that. This is variance of x1 plus a variance of x2, a prime plus a covariance of x1 and x2 plus covariance of x2 and x1 a prime. And we know that variance of x2 is just sigma 2, 2. And if you continue writing with the variables that we know, it's just sigma 2, 2 minus 1, sigma 2, 2, sigma 2, 2 minus 1, sigma 2, 1, minus 2 sigma 1, 2 sigma 2, 2 inverse sigma 2, 1. So this is just, this goes with that, and it is simplified that to sigma 1, 1 plus sigma 1, 2 plus sigma 2, 2 inverse sigma 2, 1 minus 2 sigma 1, 2 sigma 2, 2 inverse sigma 2, 1. And finally, this is equal to sigma 1, 2 sigma 2, 2 inverse sigma 2, 1. Because 1 minus 2 is minus 1. And so we have proved the second part as well, which was for the covariance. Now, with knowing this popular lemma and very important lemma, we can just start a Gaussian process, because Gaussian processes is just taking advantage of this important lemma. And in Gaussian processes, if you're familiar with, it's just supervised learning. I have another lecture about Gaussian processes. It's about 1 year ago, but now you see a more focused approach to Gaussian processes. So it's a supervised learning. What it means that you should have inputs and outputs. So this is inputs, and you have some outputs, yi. when you assume that yi is equal to f of xi, f could be corrupted by noise. But first, we assume that it is not. And then we say that, okay, yi is a corrupted by noise. So parametric representation for f, we say that, for example, p of theta. So the parametric Bayesian or parametric statistics is like that. You are familiar with that. We want to do some regression and you have a parameter. But in Gaussian processes, it's non-parametric approach because we don't have any parameter. Of course, we have parameter, but it is like an infinite number of parameters. So the idea is to do inference, and our parameters is on the functions. Our parameters, you can think of that as your output, not just the some coefficients. So the non-parametric approach is more interesting because sometimes one hyperparameter is equal to millions of finite parameters. So the non-parametric representation, your inference is like this: f condition on D. You see, f is an infinite dimensional animal because it depends on how you discretize your space. It could be, in general, it's an infinite number of points to discretize this, so it's an infinite dimensional object, we say in mathematics, and that's why understanding of that is challenging. So we try to talk about functional analysis, Hilbert spaces, Banach spaces, and create a topology on the function spaces. But now things is very easier in Gaussian processes, because if you just find some good kernels, then you have done that implicitly somehow. So you don't need very, very advanced mathematics. So that's why Gaussian process is very practical for machine learning, and even scaling of that is very successful. And many people know that infinite dimensional neural networks is equal to Gaussian processes, and so this is the tool that machine learning people use. So Gaussian processes, they define, so when I say Gaussian process, it defines a prior over functions. And the function is an infinite dimensional object, so we only need to be able to define a distribution of the function at a finite but arbitrary set of points, such as x1 till xn. So although it is infinite dimensional, but we just choose n of them, n points, n data points. And a Gaussian process assumes that the probability of x1 and f of xn is jointly Gaussian. This is very important. And we have mean mu of x and covariance sigma of x. This is the covariance. And so because it's a matrix, the element of that, for example, sigma ij, is just depends on your positive definite kernel, k of xi and xj. And the idea is that if xi and xj are similar by the kernel, then we expect the output to be similar. And in regression, the computation is order of n cubic time. I will explain later. In classification, the posterior is not exactly Gaussian. So we use approximation. So I said that we have infinite dimensional object, but we just use a finite set of points. So these finite points could be even 2 or 3. For example, I just want to use 2 test points, two training points. So x1 and x2. So they have a value. They have a value f1 and f2, and the difference of this is just the kx1 and x2, how similar they are, and also you have some output because you add noise as well, y1. And now we want to see what if I use a test input x star. What is the value of that function, which is f star, and also the corrupted one, which is y star, corrupted by noise. By noise, not oil or gas. And so these are hidden nodes. These are hidden nodes, and this is the Gaussian process for just 2 training points and 1 test points. So if these test point is similar to the training points x1 and x2, then we can write the probability that y and f conditioned on x is equal to normal of f conditioned on 0 and k of x times probability of yi conditioned on fi. So if the test points x star is similar to the training points x1 and x2, then the predicted output, which is y star, will be similar to y1 and y2. And this is the idea. And now, let prior to be f of x. We draw it from the Gaussian process having mean m of x. M of x is usually set to 0, but no problem if it is not 0. And k of x and x prime, which is the covariance function, also called kernel in the machine learning literature. And m of x is just expectation of f of x. And k of x and x prime is equal to expectation of f of x minus m of x times f of x prime minus m of x prime transpose. So for any finite set of points, as I said, just n points is enough. The joint Gaussian, the probability of f condition on x is equal to the normal f condition on mu and k. Remember that this is a vector because you have m of x1, m of x2, m of xn. So it's a vector, and this is a matrix. Kij, your kernel, k of xi and xj. Doesn't matter if your input is d-dimensional. So each of these data points could be d-dimensional. D is the size of your feature. For example, you have 1024 pixels, or you have 1 million genes, anything that you use.